So my topic for today relates with the new normal, and new normal which has brought many changes to our lives. We have been discussing a lot of aspects of new normal around business, around economics, around various different things that come. But the most important thing that I remember years ago when there was an attack on Mumbai, now we see wherever we go, we have to go through a screening process. We have to go through an X-ray screening. We have to go through some metal detectors. So that was a new normal which was set after the terrorist attack. Now this time the attack has been different. This time the terrorist is not someone whom we can see. And therefore now we have to identify the risk probably in a different way. How long are we going to impose the lockdowns? How long are we going to keep ourselves locked in the home? How long are we going to use double, triple, 4 times folded masks? How many days are we going to keep our children inside the home doing the online education? How long are we going to avoid our interactions? How long are we going to be in the nutshell and keep doing the same thing? Probably this is not going to help us in the long. Therefore, we have to bring something that has a solution where we can reduce the risk, where we can mitigate the risk, identify the risk early, and probably restrict the entry of the person who is bringing the risk into the environment which we have the changes. And that's where my speech today is. When we were starting at this early diagnostic, or when we were looking towards the requirement for screening of the people who are infected with COVID-19, currently they are using the thermal screening, and thermal screening is one of the easiest methods to fool. Take a paracetamol, wait for 15 minutes and your temperature will come down. How much risk are we putting to the people who are getting inside just based on our thermal screening? I don't think we are doing the right thing. I don't think we are doing a justice. There needs to be a foolproof method. But in the current situation, if we see the diagnostic methods which are used for identification of COVID, these methods, they are not a fit to be a screening method. First of all, they will take a long time for the results to be produced, and I don't want to speak much about the sensitivity and specificity of those results. Second important thing that comes is the requirement of skills, the medical skills, for collection of the sample and processing of those samples and to actually generate the results. The third important thing that comes is the quantity of the substrate that is required for this diagnosis. You need to actually take a very deep nasal mask, and which needs to be at least a sample which can react. And the fourth important thing that comes is, after doing all these things, there will be a biohazard, and following that, again, the sensitivity and specificity will be there because of the environmental issues which are impacting this entire outcome, this entire process. And RT-PCRs, they are so sensitive that when we are even taking a swab into an environment, and if there are certain atmospheric droplet nuclei which go and sit on that swab, there is a full probability that a false positive result will come up. So is that something that we are actually going to continue? Are we going to continue with the similar things? Are we going to make the people sit at the airport for 3 hours to get into the flight? Are we going to make the people wait for attending a wedding reception? Or are we just going to go with this thermal screening and continue with the infection risk at all point in time? Today we have COVID, tomorrow if some other virus comes, what are we going to do? Are we going to still continue with the same problem? There has to be a stop, and there has to be a new normal to this. And that new normal actually will come from what we actually need. We need something that is as simple as detection of the problem or detection of the pathogen within the breath or within its natural state. Suppose if some virus is infecting through the fecal matter, it should be tested there. If something is spreading through the breath or the droplet nuclei, it should be tested there. And the result should be reliable. I will not say specific. It is not a replacement for diagnosis. It is not a replacement for any kind of diagnosis method. It should be a screening. If there are false positives, it is okay, but there should not be false negatives. And that is where the need of the hour is. And no method currently is actually meeting this requirement. And that's where come our original thoughts. I was reading Nasadiya Sukta some time ago, and Nasadiya Sukta tells us to challenge everything that we have. Anything that is in front of you, keep challenging that. And that is what we started doing. We started challenging why and why not. If the antibodies are present and if we are currently utilizing antibodies, if antibodies is the most specific way of diagnosis, why can't we use them with a breath? If there are the technologies in the world which can use breath, which can use smells, which can detect smells, there is a technology which can identify the smell of some particular substance and identify, okay, something is rotting. Why is that same technology not be used with diagnosis? And when we started doing this, we started looking to multiple different type of sensors. There are multiple different type of sensors, and one of the sensors which is there highlighted first, that is in my hand, maybe I'm just showing it to the camera, I don't know whether it can be seen. So this kind of sensors are the nano sensors, and we have been looking to these options. There are multiple ways with which we detect smells today, where we do the processing of various type of samples. We do the processing of various different types of micro sensing. We use them as the biosensors. If we see, there may be a lot of things which are available. These are a few types of sensors which we had discussed. We discussed the electrical impedance or the current based sensor with Professor Siddharth Tallur in IIT Mumbai, and he has filed a patent with a PCB electrode based detection of infections. Similarly, there is another way, that is MEMS, that is microelectrical mechanical system, where we can utilize the cantilevers to detect the smells, and this is also one of the most common technology which is used for smell detection. Similarly, there can be nanophotochemicals, like we all know what is ELISA. ELISA is one of the standard diagnostic methods, and this diagnostic method can definitely be utilized for a very specific reason. This in a micro way can give a fluorescence outcome, and we can still identify the pathogen in this environment. Then there are certain micro-optics. I forgot to mention that in BITS Pilani, Professor Inamur is the person who is actually working on this technology in various different modes. Then there is micro-optics. This technology was invented by Professor Soumya Mukherjee of IIT Mumbai, and this technology is one of the simplest technology which can easily be retrofitted for any kind of antigen-antibody reaction. And then other than these four which are based upon antigen and antibody, there are technologies which are based upon spectroscopy. Raman spectroscopy is one of the best methods which is currently utilized for identification of various types of smells. And this technology can be utilized, or can this, rather, let me put it other way, can this technology be utilized was our question at that time, and we identified that all of these can be utilized as the technologies for detection of COVID-19. The question is how. Now for that how question, I have taken an example which we were working with Professor Siddharth Tallur in IIT Mumbai. There can be multiple things that we can put on an electrode to detect the COVID-19 infection. Like what we do for smell today, we coat the electrode with an antibody, we take the substrate, put the substrate on the electrode, put a conducting material on that and record. If that material is reactive, suppose if I am detecting the smell of orange, I'll put the antibody for the smell of orange, and if there is a smell of orange present, that electrode will become active. What we did, we tried various different type of materials. This, when I say tried, that doesn't mean physically trying. We actually did a feasibility of this, and there could be various type of things, like we could have synthetic antibody materials. like D-dimers. It could be something which is mechanical binders like the plated or the marked antibodies. It could be something which could be pre-bound proteins, and that could be something that is very simple like a natural antibody which we get when we get an infection. And there could be any other things, and based upon all these things we did a feasibility. And this feasibility resulted into identification that natural antibodies are the best things that we can use, and this was our hypothesis. We were trying to understand whether the natural antibodies are going to work on the electrode. How are they going to bound? What type of results are they going to give? Are they going to vary according to the quantity? Are they going to be enough to be detected in the given technology? And this all feasibility we did, and this was supported again, as I said, by Dr. Siddharth Tallur, Professor Siddharth Tallur of IIT Mumbai. And then we identified that yes, this technology works. But this technology is something that was very new. The feasibility was done. COVID is a heavy virus. COVID is a virus. Coronavirus is something that can give me a result probably in a small substrate. But not all are going to give the same results. Cantilever works on gravity. Probably if my antibody weight is too much, and on that if even one particle goes and attack, it is going to give me a full deflection, which can be a hypersensitivity. If it is fluorescence, coronavirus has a low reactivity. If I use it with a fluorescence kind of thing, is that fluorescence going to be enough? So there were many questions, and these many questions we started looking towards the scalability of this in the future. Today I have coronavirus, tomorrow I may have some other virus which may be a smaller. Some time ago there was a bird flu, after that there was a swine flu. If I want to detect this also in the breath or in the atmospheric air, are they going to support, are these technologies going to support me there? So therefore the next question that came to me was how to make it universal, how to make it applicable to everything, how to generalize it. And therefore we kept brainstorming, and then we understood that one technology is not something that fits everything. It has to be a combination of a right sensor, the right antibody, the right mode of collection with a natural substrate. I'm insisting on the word natural substrate. If spread is through breath, breath is what I need to test. If the spread is through gastrointestinal fluids like stools or vomitus, it has to be tested. And therefore, the technology which uses the respective substrate in their natural form and the antibodies, the quantity of antibody versus its molecular weight, its immunovalency with the given virus, bacteria or whatever pathogen, these all things were put together, and then we came up with a formula which gives me the actual quantity required for the antibody, its weight and its activation time which is required on the electrode, and the principle of electrode being tested with that type of substrate or the or that kind of quantity. So putting all elements together, I understand whether that technology is going to work or not. If it is working, what will be my range of success? And with that, we've recently filed a patent which is now published also. So this was the sensor technology, or this was the retrofitting of the smell detection technology along with my routine pathological conditions or routine pathological testings of the antigen-antibody reaction. These two technologies were fused, and this new method of screening diagnostics at the doorstep or maybe at any crowded place that was introduced. This technology can be universalized. We can use this with a swab on any parcel that comes in. We can use that into the AC vents like a smoke detector, and there we can do it. It can be used on the roadside, like we see the police holding the handheld device and getting this, the sample, breath sample of the people to see whether there is alcohol or not. Same thing can be done for these infections also. And tomorrow if some new infection comes in, just simply the replication of the protein of the antibodies present in the first ever case can be done. I take this blood sample of the person, isolate the protein, replicate that protein, make those antibodies and start diagnosing. So infection can be very quickly covered and can be very quickly arrested at a very early point if this technology becomes universal. Of course, there is a long way to go. There are the scientists who are working. I have already mentioned the names of Dr. Ajay Agrawal, who is now a part of IIT Jodhpur, who was earlier a part of CIRI. They have also done a similar project where they have used artificial intelligence with Raman spectroscopy to identify if there is a new infection which comes in, which can be identified on an immediate basis. So we don't need to wait until the antigen-antibody reaction also to come in. If we know what harms or if we know what doesn't harm, we can properly create the range of acceptance and can allow or disallow a person, an animal, a pet, or anything that is a source of potential infection. Thank you.